so what's happening now in part D? X is going off to infinity again. What's happening in the numerator? Well, as x goes to infinity, the sine of 2x is just going to be doing what it always does. It's just going to be wiggling back and forth between -1 and 1. The denominator, however, is going to infinity. So this is like one we saw in class, where we have a bounded function in the numerator and an unbounded function in the denominator. This is the prime candidate for the squeeze theorem. I know that no matter how hard x tries, the sine of 2x is always trapped between -1 and 1. And since the square root of x is always a positive number, well, or 0, but x is heading towards infinity, the square root of x is always going to be a positive number. That means I can go ahead and divide through by the square root of x. And this is the dangerous step, because normally we don't like to multiply or divide through by variables. So I'm going to put this in red. Why is this true? The square root of x is a positive number as x goes to infinity. Right, that's why I can get away with doing that. Now it's time for the old squeeze play. As x goes to infinity, what's happening on the left bound? This is going to 0. On the right bound, this is going to 0. So what's inside has no choice but to go to 0. So by the squeeze theorem, the limit as x races off to infinity of the sine of 2x over the square root of x is 0. And this is another good opportunity to actually use the graphing calculator. It would behoove you at this point to graph 1 over the square root of x, -1 over square root of x, and sine of 2x over the square root of x. And what you'll see is this damping sort of phenomenon that's happening. And so you'll actually see that the sine of 2x is going to get squeezed, or sine of 2x over square root x is actually squeezed then between the curves y equals plus or minus 1 over square root x. So that'll do it then for part D, and that'll do it then for number 1. All right, in number 2 now, we're asked to sketch the graph of a function which satisfies all of the following criteria. So we've got 8 criteria listed. And I think the best way to approach these kinds of problems is to go ahead and draw a big old axis, xy axis, and we'll try to just check off each of these at once. The limit as x goes to -infinity of f of x is 5. Okay, so that means I've got a horizontal asymptote at y equals 5. I'm just going to dot that in. Y equals 5. Now, it doesn't tell me how I'm approaching 5. I don't know if it's coming in like this or if it's coming in like this. All right, I don't know, so I'll just pick one and live with it. So I'll say it's coming in this way. The okay, so that's taken care of. The next ticket item, x approaching -2 from the left of f of x is 3. X approaching -2 from the right of f of x is 1. All right, so, okay, that's 5, 4, 3, 2, 1. And we'll do -1, -2. And I'm coming in -2 from the left. It's getting close to 3. Okay, so I don't know if I fill in that or not. All right, so coming in from the left, I'm getting close to 3. All right. Coming in from the right, I'm getting close to 1. So when I come in this way, I'm getting close to 1. Okay, so that's pretty much what I have there. As I come in from the left, I'm getting close to 3. Coming in from the right, getting close to 1. So that takes care of those 2 items. The limit as x goes to 1 of f of x is -infinity. Okay, so here's x equals 1. Now, notice that there's no plus or minus above that 1. That means that when I come into one from both directions, I'm heading to negative infinity. So I've got a big old vertical asymptote there. And on both sides, I'm heading to negative infinity. So that's what that means. The limit as x goes to 3 of f of x is 2. Once again, there's no plus or minus there. So that means as I get close to 3, I'll say 1, 2, 3. I'm getting close to 2. So there's 2. And once again, that's from both directions. So I sort of have that going on there. And last but not least, the limit as x goes to infinity of f of x is negative infinity. So my far right end behavior, I'm heading downward again. Okay, so those are what's happening. Now I try to see how I'll connect these up. It says the domain of f is minus infinity to 1, union 1 to 3, union 3 to infinity. Okay, so what's that really telling me here? It's telling me that the hole at 3 is never going to get filled in because the function's not defined at 3. It's not in the domain. The function also isn't defined at 1, so there's going to be no dot I fill in there. But that's it. So in other words, I'm going to be able to fill in the dot somewhere at the 2 because 2 is in the domain. I just don't know what dot to fill in yet. This is where the intervals of continuity come in. F is continuous from minus infinity to minus 2. All right, so that means I can just connect these parts up with a nice connected curve there. And this is the right here. This bracket on the negative 2 tells me that I'm continuous from the right at negative 2. So that means I actually fill that dot in at 1. And then it's continuous over to 1. So I can connect that up. It's continuous from 1 to 3. So that means I can connect this curve up. And then it's continuous from 3 to infinity. So on the intervals where it's continuous, I connect it up in a nice connected curve, and there you have it. So that's one possible answer. There's many possible answers that satisfy all these criteria, but that's one. So that'll do it for number 2, and that'll do it then for checkpoint quiz 5.